Hello and welcome to the All Hands EPSCoR meeting. My name is Parnian. I'm a postdoc in Nejat Lab and Center for Biocatalysis and Bioprocessing at the University of Iowa. The project that we are working on is developing a generalized developability model for proteins. And this presentation is a brief overview of our first year milestone, which is setup and optimization of the KDDLS or dynamic light scattering method for studying the interactions of proteins. To give you a little background on this topic, generating novel antibodies often lead to identification of thousands of potential candidates, which after a couple of screening rounds can be narrowed down to several antibodies with the desired characteristics. But resource-intensive steps like development of a cell line, designing a manufacturing process, or formulation can be carried out for only one candidate. Therefore, another screening step can be used to find this ideal candidate, and this step is called developability assessment. This developability assessment can be defined as the likelihood for the successful development of a lead candidate into a stable, manufacturable, safe, and efficacious drug. So developability can be carried out through a set of small-scale, fast and predictive tests that may cover several areas, including post-translational modifications on charge, chemical stability, self-interaction and aggregation, or pharmacokinetics. Here in our research, we are more focused on self-interaction and aggregation of proteins and use dynamic light scattering for the developability assessment. And dynamic light scattering, or DLS, technically measures diffusion coefficient from which effective hydrodynamic radius can be determined. So DLS basically monitors the fluctuations in light intensity resulting from scattering of light from particles undergoing Brownian motion in a solution. So as particles move randomly in the solution, the scattered light changes and interacts with a detector, which converts the changes in the light intensity to a signal that can be translated to diffusion coefficient, which later can be used to determine the size of protein molecules, polydispersity of the solution, biomolecular interactions, and thermal stability. So with DLS, we can evaluate diffusion coefficient as a function of solution concentration and determine the diffusion interaction parameter, or KD, which is a single molecular descriptor well suited for high throughput measurement of colloidal interactions. In other terms, we can generate samples of an antibody or protein with different concentrations in a desired buffer and use DLS to measure the diffusion coefficients of these samples. Then, by plotting the diffusion coefficients versus concentration and performing a linear regression, the ratio of the trend line's slope to the y-intercept gives the diffusion interaction parameter, which can be used to assess the type of molecular interactions in terms of being attractive or repulsive. And diffusion interaction parameter has been consistently linked with biophysical properties like viscosity, opalescence, and aggregation rate in high concentration liquid formulations, and can be used to screen basically good behaving candidates in terms of these properties. So we have been using this KDDLS method to assess the colloidal interactions of different monoclonal antibodies. Here you can see our results from testing 8 different antibodies in a graph of diffusion coefficient versus concentration. And the first interesting observation here is that different antibodies behave differently in terms of colloidal interactions, as you can see different trends in diffusion coefficients versus concentration, which can be translated to KD to evaluate the antibody's behavior in a solution. The second interesting observation, which we're focusing on for this research, is that, as you can see, as the concentration decreases, the diffusion coefficient of all the antibodies tend to converge. This behavior is expected because at lower concentrations, the molecular distances are larger, and therefore it is reasonable for the diffusion coefficient to have smaller variabilities. With this, we hypothesized that at 1 milligram per milliliter, which is our lowest concentration here, the diffusion coefficient for the antibodies with relatively similar molecular weights can be assumed similar. To test this, we performed statistical analysis of the measurements at the lowest and highest concentration and observed that while at 5 milligram per milliliter, all the antibodies had statistically different diffusion coefficients. At 1 milligram per milliliter, only 6 antibody pairs from a total of 28 had different diffusion coefficients, and the differences were caused by 1 or 2 antibodies that had a slightly different molecular weights than others. So with this assumption, we are investigating a method that uses a single concentration measurement of diffusion coefficient for predicting protein solution behavior instead of multiple measurements. This method is promising because it increases throughput, it can decrease sample volume, and also decrease the error associated with multiple measurements required for the conventional KDDLS method, and also may be applicable to a broader range of antibodies or even non-antibody proteins if we could address the effect of the molecular weight. So in our second hypothesis here, we assume that by normalizing the diffusion coefficient with the molecular weight based on this empirical equation, this method can be generalized to more antibodies as well as other kinds of proteins. We tested this and included test results from bovine serum albumin as a non-antibody protein and repeated our statistical analysis. And this time, all the protein pairs had statistically similar diffusion coefficients at the lowest concentration, while the measurements were significantly different at the highest concentration. And this confirms our second hypothesis. So with that explained, our future milestones are to first test this method on various proteins and define the technical specifications for the proposed method in terms of sample concentration, volume, throughput, buffer and pH, and temperature. And eventually, we plan to validate the predictive power of the proposed method in terms of colloidal interactions and protein self-association by comparing it to the conventional KDDLS method, and also perform direct validation through viscosity measurements. With all that explained, thank you very much for your time. I hope this was a useful presentation for you.